We now begin Lesson 4 for the chapter on the atom and the elements. Again, let's briefly review what we discussed in the last lesson. We talked about the subatomic particles that comprise an atom. We talked about a proton, neutron, and electron, and their mass, the mass in AMU units, and charge, the fact that a proton has a charge of +1, an electron has a charge of -1. And we also explained the concept of a mole and Avogadro's number. Do you remember Avogadro's number, in case you have to give him a call? 6.02 times 10 to the 23rd. Now, in this lesson, we're going to go back and talk about how the structure of an atom was determined, or a little bit about how it was determined, because the previous lesson we sort of jumped out and explained that these subatomic particles existed, but we really didn't describe the history of, or how they were discovered. And if you recall, we in one of the early lessons we talked about the ancient Greek philosophers Leucippus and Democritus, who had rationalized that there must exist the smallest uncuttable particle called an atom. But then for the next 2,000 years or so, scientists really did not embrace the concept of an atom until in the 18th and 19th century. There were a number of very important scientists. We won't go through all of these: Robert Boyle and Antoine Lavoisier. But let's pick up with a chemist named John Dalton. Now, John Dalton was studying chemical reactions, and at the top of the slide I have represented a typical chemical reaction. Two hydrogen gas molecules, H2 for hydrogen gas, reacting with oxygen gas, one oxygen gas molecule, to form two water molecules. And what scientists such as Dalton were studying around this time was the fact that chemical reactions seem to occur in definite proportions. That is, the reactions always seem to involve two parts of hydrogen reacting with one part of oxygen to form two parts, or two molecules, of water. Now, based on these types of observations, John Dalton proposed in 1808 the atomic theory of matter, which has the following important tenets: that all matter is made of atoms, and that for an element, all the atoms of an element are identical, and that a compound such as water, is formed by two or more elements combining together in some way, such as the reaction above, and that chemical reactions involve, in general, chemical reactions involve a rearrangement of atoms in a molecule. Now, over time, our models for an atom have evolved quite a bit. Based on John Dalton's arguments, an atom might be something simply like a marble, and marbles of different sizes. That is, remember back to the periodic table where we had the smaller elements at the top row, and then as we go down the rows, the atoms would get larger. But the atoms could simply be small spherical particles. That's because at the time of John Dalton, the subatomic particles were not known. It took other scientists, such as J.J. Thomson, to discover the fact that there existed electrons and protons, charged species, such as an electron. And so at one point we had what is called the plum pudding, or the Thomson model, in which the positive protons and the negative electrons were thought to be balled up together in what it was called a plum pudding model. Other scientists who followed, Ernest Rutherford, further helped us characterize the structure of an atom by performing experiments where he would shoot alpha particles at an atom, and he discovered that most of the time when he would do this, the alpha particles would go right through, but occasionally, very rarely, but occasionally, the alpha particles would bounce right back at him. And so he concluded, based on these experimental studies that there is a hard center to an atom, and that hard center is what we now call a nucleus. Niels Bohr followed along. He came up with one of the most revolutionary interpretations of nature, that energy levels are quantized. In particular, the energy levels of electrons in an atom are quantized, meaning that they exist at discrete energy levels. Now, this was very revolutionary type of thinking, because up to that point it was thought that energy levels, regardless of what type of energy levels we were talking about, would be a continuum. But he described these energy levels as if they were steps on a stairs, as discrete levels, and that turned out to be the model that helps us explain the nature of atoms. Erwin Schrödinger followed by further refining this model to explain that the electrons that were orbiting the nucleus of an atom, were not simply acting like planets orbiting the sun in like circular orbits, which the Bohr's model would have been consistent with that. But Schrödinger's interpretation was that the electrons were swarming around the nucleus, almost like bees swarming around a hive, and there were particular orbital patterns that existed, but that they weren't discrete circular type of orbits like the planets orbiting the sun. So we had this progression of models of the atom over the years. At the present time, our understanding is that protons and neutrons form the nucleus, the hard core center of an atom, and that electrons fly around in orbits, sort of in an electron cloud type of orbits. That most of the mass of an atom is in the nucleus. Remember, the protons and the neutrons weigh much more than electrons, electrons being only 1/2000th of the mass of protons. So most of the mass of an atom is in that hard core nucleus. Now, to give you some idea, because when we're talking about atoms, things are so small that it's oftentimes hard for us to even rationalize this. If a hydrogen atom were the size of a marble and were placed on the middle of the 50-yard line of a football field, the electrons would be swarming around, whizzing around the stands. Just to give you some idea of the dimensions and the fact that most of an atom is empty space. Most of it is empty space. It has a dense nucleus and then electrons whizzing around in a cloud. Now, this table shows the first 10 elements of the periodic table. As I mentioned to you earlier, there are 114 or more elements. We don't really need to know that many, but we need to know a little bit about how they are described. If we look at the first 10, hydrogen, helium, lithium, beryllium, the identity of the element is determined by the number of protons. That's important. The identity of the element is determined by the amount of protons. Now, usually there are about the same number of neutrons as protons, but notice for our very first one, hydrogen, most of the time has a single proton and 0 neutrons. And if you look down the list, you see others where lithium has 3 protons, but most of the time it has 4 neutrons. So the number of neutrons is not always identical, although it's usually close. So the identity of the element is determined by the number of protons. Now, also, if you look at the last column, the number of electrons is the same as the number of protons for the neutral form of the element. Now, what I'm trying to stress is that electrons can either be gained or lost, and we'll get to that in a next chapter. But, for example, lithium has a tendency to lose one of its electrons. If it does, it forms what we call a cation, C-A-T-I-O-N, cation, lithium plus 1. Another example is fluorine tends to gain an electron and become fluoride minus 1. This would be called an anion. So Most of the time, the number of electrons is equal to the number of protons, except when we form either a cation or an anion, in which we either lose or gain electrons. Now, getting back to the number of neutrons and protons and how they're usually about the same, but not always. Also, it's important to point out that there exist what are called isotopes. And let's go to the next slide to explain this a little more. Many elements have more than one isotope, and an isotope is a form of an element that has different number of neutrons. And the best way to explain this is by an example. Let's consider hydrogen, the very first element. Hydrogen actually exists as 3 possible isotopes. Now, by far, the most prevalent one is the simplest isotope that has just a proton in its nucleus, no neutrons. So just a proton in a nucleus and 1 electron in its electron cloud. But there can exist another isotope, or there does exist another isotope called deuterium, which has in its nucleus both 1 proton and 1 neutron. And there can also be made another isotope of hydrogen called tritium, which has 2 neutrons in a nucleus in addition to 1 proton. Now, all 3 of these are hydrogen. They share the physical properties of hydrogen, but there are some slight differences, and in particular, the one called tritium is unstable, meaning that its nucleus will break down, undergo what is called a nuclear reaction, a phenomenon which we call radioactivity. Now, what is interesting about the radioactivity of tritium is that it takes a long time for it to undergo this nuclear decay. It takes 12.3 years, so that seems like a long time. Another element that has an unstable isotope is that of carbon, carbon-14, which undergoes a nuclear decay on an even longer time scale of 5,730 years. And there are other isotopes of elements that are radioactive or unstable, and we'll talk about those later in different chapters and how they can be used productively to determine the age of various things. We'll now have a break and for a brief few questions for you to answer, and then we will pick up with a lecture on a little bit more of the historical side of some of the discoveries of the elementary particles that comprise an atom.